So in 9.7, we're going to be looking at Taylor polynomials and approximations. So what a Taylor polynomial is a polynomial of some given degree or some given order that is used to approximate some function that's not a polynomial. So for example, we might want a polynomial that approximates the function e to the x. And there are various reasons that we might want a Taylor polynomial. We might, with polynomials, they're easy to differentiate, they're easy to integrate. Lots of things with algebra are easier to do on polynomials versus some other types of functions. Um, they are just going to be approximations, though, because for most functions, we're not going to be able to come up with a polynomial that is a perfect match of this function. As we get farther on, then we're going to look at Taylor series, which is basically going to be a polynomial that goes forever, that goes to the nth power as n goes to infinity. And as you get more and more terms, we get to where we have a better and better and better approximation to this function. So in order for it to be a good approximation, at a given value of the function, we want that to be equal to our polynomial at that same value. If we take the derivative at that particular x value, we want it to equal the derivative of our polynomial. If we take the second derivative, we want the second derivative to have the same value for the polynomial and for the function, and so forth. Now, C is the center of our polynomial. It's the location where the function and the polynomial are exactly the same. But the farther we get away from C, since we are going to have some error, then they're not going to be exactly the same anymore for most functions. So if we want to find out, for example, values of f of x equals e to the x, and we want to find values near x equals 0, then 0 is going to be our center. Then we will want our polynomial at 0 to be the same as e at 0. And we'll want the first derivative of our polynomial to be equal to the first derivative of e to the x at 0. We might later, once we get that polynomial, we might evaluate it at points close to 0, 0.1, 0.2. And they're going to be fairly close. They may not be exactly the same as our original function, but they should be close as long as this point is close to where we are centering it. So let's see how we could do this. So the function that we're going to compare it with, and that we're going to find a Taylor polynomial for, is f of x equals e to the x. And let's do a fourth degree approximation. So we want a constant term, an x to the first, an x to the second, an x to the third, and an x to the fourth term. And we're going to center it at 0. If it's centered at 0, then more specifically, it's also known as a Maclaurin polynomial. Taylor polynomials can be centered anywhere, but specifically, if it's centered at 0, that's referred to as a Maclaurin. So we need our first derivative, which happens also to be e to the x. Our second derivative, which is e to the x. Our third derivative, which is e to the x, and our fourth derivative. Now, this is the reason we started with this one, because our values, our first derivative, second derivative, third derivative, these are all simple ones to do. If we are centered at 0, then when we plug a 0 into our function, we get 1. In this case, if we plug a 0 into our first derivative, since it's also e to the x, we get 1. When we plug a 0 into our second derivative, we get 1. For our third derivative, we get 1. And for our fourth derivative. Now that's not going to be true with most functions. For most functions, we're going to get different values here. But just to illustrate how this is going to work, then we just use a simple function. Notice if we plug a 0 into our polynomial, every term that has an x in it, if we plug a 0 in, that would be 0, that would be 0, that would be 0, and that would be 0. So when we substitute a 0 into our polynomial, we get a sub 0, which that has to equal what our function equals at 0, which is 1. So that means a sub 0 is 1. So our polynomial to this point is 1 plus a sub 1 times x plus a sub 2 x squared, a sub 3 x cubed, a sub 4 x to the fourth. Now we need our first derivative down through our fourth derivative. So our first derivative, the derivative of a constant is 0. So then the derivative of the next term is a1. Then we have 2a2x, 3a sub 3x squared, 4a sub 4x cubed. If we substitute a 0 into there, every term that has an x in it is going to be 0. So we get a1. And that needs to equal our first derivative at 0, which in this case is 1. So a1 is also 1. Now if we take our second derivative, and I'm just going to go back here, the derivative of a constant is 0, so we're going to get 0 plus 2a2. For the next term, we would bring this 2 down, so we would have 3 times 2, a cubed x. For the next term, we'd bring the 3 down, and we would have 4 times 3, a to the fourth, x squared. If we plug a 0 in there, this one, and excuse me, that one would be 0. So we would get 2a2, and that would equal our second derivative at 0, which is 1. So a2 would be 1 over 2. Excuse me. To get our third derivative, we go back here to the second derivative and take the derivative. So the derivative of a constant is 0. The next term is 3 times 2 times a sub 3. The next one, we bring the 2 down, and we would have 4 times 3 times 2, a sub 4x. And I'm leaving that as 3 times 2 and 4 times 3 times 2 for a reason, to help us see a pattern that we're going to get to momentarily. Normally you would multiply that out, but in order to better see our pattern, I'm just leaving it. So when we substitute a 0 in there, we would get 3 times 2 times a sub 3. That should equal the third derivative of f at 0, which is 1. So a sub 3 is 1 over 3 times 2. And then lastly, our fourth derivative of the polynomial would be 4 times 3 times 2 times a sub 4. When we substitute a 0 into that, we would get 4 times 3 times 2 times a sub 4. That should equal f fourth derivative at 0, which is 1. So a sub 4 is 1 over 4 times 3 times 2. So our fourth degree Taylor polynomial is a sub 0 plus a sub 1x plus a sub 2 x squared plus a sub 3 x cubed plus a sub 4 x to the fourth. And of course we could multiply those out, and we could call that 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the fourth. So that polynomial and f of x equal e to the x, those are going to be exactly the same at x equals 0. They're going to touch there because they have the same y values. Their first derivatives are the same, which means they have the same slope. They have the same concavity, the same third derivative, and the same fourth derivative. As we get farther away from 0, our polynomial and our function are going to look less and less alike. But for a certain window, they're going to be close approximations of each other. Let's take a look at a graph of these two functions. If we come over here, then the blue curve is our polynomial. The red curve is e to the x. So the red curve is our original function, and then the blue curve is our approximation. So notice when x is 0, those are the same. And if we're pretty close to x equals 0, then the curves are right on top of each other. But the farther to the left we go, eventually our curves diverge from each other. E to the x keeps going down with a horizontal asymptote while our polynomial turns. As we go farther to the right, our polynomial is a pretty good approximation, but the farther over we go, we get a little bit more and a little bit more error. So the polynomial and e to the x are really close to the same in this window in here, but as we go farther and farther, it becomes a not as good of approximation. So if we need an approximation that's better, we might need more terms, or we might need to adjust where it's centered at. If we look at our coefficients, remember the reason that these were 1 was because that's the value of our nth derivative, and then we were to get our a sub 4, for example, by itself, we're dividing both sides by 4 times 3 times 2. That would be divided by 4 times 3 times 2. So that numerator is the fourth derivative at 0, and on bottom we have 4 times 3 times 2. That's how we got a sub 4. If we look at a sub 3, same thing. This number is our third derivative at 0. That is on top, and we divide by 3 times 2. So this is our third derivative at 0 over 3 times 2. If we go back to a sub 2, it's our second derivative at 0 over 2. A sub 1 was our first derivative at 0, and it was just that, but we could say that was over 1. And then what about our 0th? Well, that was our function at 0. But notice our denominators. We could put a 1 there, a 1 there, a 1 there. 3 times 2 times 1, that's 3 factorial. 4 times 3 times 2 times 1, that's 4 factorial. This is 2 factorial. This is 1 factorial. Well, we could also call this one 0 factorial because 0 factorial is 1. So to get our nth coefficient for our Taylor polynomial, we take our nth derivative at our center and we put it over n factorial. So that's the formula of how we get our coefficients. To get our polynomial, it's our first coefficient, our next coefficient, times x, and depending on where it's centered at, when it was centered at 0, it was just x. But if it's centered somewhere else, it would be x minus c. And we would go for however. Now you might say y x minus c. If we are centered at, for example, 2, then we would have some constant plus a sub 1 x minus 2 plus a sub 2 x minus 2 squared plus a sub 3 x minus 2 cubed plus a sub 4 x minus 2 to the fourth, and however far we want to go. Notice if we plug a 2 into that polynomial, not the function, everywhere we have an x minus 2, that's going to be 0. And remember, that was one of the key things excuse me, that allowed us to get our a's, was that the number we were plugging in for x made all of these other terms 0. When we plugged a 0 in for x here, all of those were 0. So if our center is not at 0, we subtract the center from each x so that when we plug that number in, that factor makes 0. When we take the derivative of, let's say, this one, we bring the 2 down, x minus 2 to the 1 less power, so we still have that factor, x minus 2. So when we plug a 2 in, every one of those terms that have a factor of x minus 2 are gone, and we're left with just the coefficient. So this is the general form of a Taylor polynomial, and this is how we get the coefficients. So we're not going to have to every single time take all of these derivatives of the polynomials. We will have to take the derivatives of the functions and find out the value of the functions at the center, but not of the polynomial. This formula will give us our coefficients that we need without having to repeat that. So let's do an example. Let's suppose we have f of x equals cosine, and we want to find a 4th degree polynomial. We want to find a 4th degree polynomial, and let's say that we want it centered at pi over 2. So 4th degree. And let's change this to c instead of x. So if it's 4th degree, we need 4 derivatives. So our first derivative would be minus sine. Our second derivative, the derivative of sine is cosine, so leave the negative up front, and the derivative of sine is cosine. For our third derivative, we have a negative out front. The derivative of cosine is minus sine, so we get sine. And our fourth derivative, the derivative of sine is cosine. So we're actually back to the original function we started with. So when we substitute our pi over 2n, cosine of pi over 2, cosine of 90 degrees, or pi over 2, is 0. If we plug it into our first derivative, sine of pi over 2 is 1. We still have the negative in front of it. When we put it into our second derivative, cosine is still 0. When we put it into our third derivative, we get sine of pi over 2, which is 1. When we plug it into our fourth derivative, cosine of pi over 2 is back to 0. And let's actually go to 5. So our fifth derivative would be minus sine. So our fifth derivative at pi over 2 would be negative 1 again. So we're going to use those values to get our A. So let's bring these down here. Remember, A sub n is the nth derivative evaluated at C over n factorial. So A sub 0 is the 0th derivative at pi over 2 over 0 factorial. Well, the 0th derivative means we haven't taken a derivative, it's just our function. So when we plug pi over 2 into our function, we get 0. 0 factorial is 1. So the first coefficient is 0. Our next coefficient is the first derivative at pi over 2 over 1 factorial. So that's negative 1 over 1, or negative 1. Our second coefficient is our second derivative at pi over 2 over 2 factorial, which is 0. Our third, a sub 3, is our third derivative over 3 factorial. So that's 1 over 6. A sub 4 is our fourth derivative over 4 factorial. And then a sub 5 is our fifth derivative at pi over 2 over 5 factorial. So that's negative 1 over, I think that's 120. That's 2, 6, 24 times 5 is 120. So those are our coefficients. So our fifth degree Taylor polynomial would be a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared plus a sub 3 times x minus c cubed, a sub 4 to the fourth, and then a sub 5, oops, a sub 5 to the fifth. So this would be a fifth degree polynomial. There would be an approximation for cosine. Of course, that's gone, that's gone, that's gone. So our polynomial simplifies to minus x minus pi over 2 plus 1/6 x minus pi over 2 cubed minus 1/20th x minus pi over 2 to the fifth. So if we graph that side by side with cosine, then near pi over 2, they're going to be very comparable. Now let's compare our graphs. So if we go to here, the blue curve is cosine, y equals cosine x. The red curve is our polynomial, our fifth degree Taylor polynomial. Notice cosine, that's just a wave. And for a while, our polynomial is pretty good. We're centered at pi over 2. Pi over 2 is right here. So notice for a while, our polynomial and our cosine wave are almost exactly the same. Same thing this way. So there's an interval in here for which is a very good approximation. But once we reach a certain point, our polynomial is not going to be a great approximation. If we put a 6 into our p of x, we're going to get a y value down here, where if we plug in a 6 to cosine, we get a point up here. So those are two completely different y values. Where if we plug a 3 into our function or our polynomial, they're almost the same value.